In looking at the graphs of polynomials, lesson 4 of chapter 3, you're going to see a lot of similarities to all the things that we had done with parabolas. We did a lot with parabolas. And so you're going to see a crossover. So maybe it won't be that difficult. Now, now there's two people. Maybe what if I just leave everybody out in the lobby until the end of class? Because all right, hopefully that's it. Try this again.
The internet's a little slow, right, sir?
What's that, Moises?
The internet's a little slow.
The internet is going slow?
Yeah.
Oh, our school internet, according to a student, is our internet is going slow. That must mean he's not having a good time. He's stuck with what we have here. Okay. As I mentioned, we talk about polynomials, and if you recall, y equals, that's not right, y equals x squared is a polynomial, second degree. It shifts left, it shifts right, up and down, it stretches vertically, it shrinks vertically. All polynomials will do the same thing. So we're starting out by looking at just the kind of like a parent function, ax to the some power. So that really is only the first term of a polynomial. It could be y equals 2x squared, y equals to 1/2 x to the 7th. So that's all we're looking at is the leading term and looking at what does that leading term tell us. So the first three pictures that are given to us are, let's see, he wants me to look at them. Somebody else is knocking at the door. And somebody else is knocking at the door. Guys, you really need to try to get to class closer to the announcements time because I can't stop teaching every 30 seconds. You know, you're gonna, and then if you're not in the class and put your name in, I won't even know you're even here. So if you just came in, make sure you put your name in the attendance so that I know that you are in the classroom. Okay. And I'm not doing the attendance till after I'm done because I keep getting stopped anyway. All right. So here we go again. Three graphs. He wants me to answer these questions. Each graph above has blank degree. Well, let's look at the degrees. That degree, I don't see a number, so it must be 1. And by the way, I can tell if it's supposed to have an A in front, A in this case must be a 1. I think he's made all these A's equal to 1. N is a 3, third degree. N is 5, that's fifth degree. And I want you to notice something. They all look very similar in one way. They all start from the bottom left and go up that way. They all do. Pay attention to that. That's important. So each graph above has what kind of degree? 1, 3, and 5. What would you call those three numbers? What kind of numbers are they? Louder.
They're odd.
They're odd. They certainly are. They're strange little buggers. They're odd. They're odd degree. And we talked about that before because if they have an odd degree and we call that an odd function, and it exhibits symmetry about do you remember the symmetry was, look at this case. If I put a pin on this, cut this thing and cut it right here, and push it and rotate it, this piece lines up to this piece. Or if I cut it right here and I rotate it all the way around, it comes back to the beginning again. So it's symmetry around what? Around what? I'm putting a dot there. Say it again.
The origin, symmetry around the origin.
It absolutely is symmetry around the origin. That's what an odd function does. We had that lesson before. And each one of these, each has domain. I'm going to put the domain looks like any x to the left and any x's to the right. All three of these look that way. So I'm going to write in parentheses negative infinity, infinity. And then the range is all the y's. Well, it looks like it goes far down forever and up forever. So that also will be negative infinity to infinity. And he gave us three different odd functions, polynomials, and they all had the same domain, the same range. And they all had the same, how it's kind of increasing from here to here. And they're all continuous on the entire domain of negative infinity to infinity. Additionally, these, I don't know what else to put. I think somebody yesterday said, just use the word odd again. Okay, these odd functions, I hate repetitiveness. These odd functions are blank on their entire domain, appearing as they blank. Okay, these functions are increasing. Remember, that means as you go from the left to the right, every y value is greater than the one before it on the entire domain of negative infinity to infinity. And it appears as though they fall to the left and they rise to the right. Fall to the left, rise to the right. Every one of them seems to do that. That's what he said. It appears to do that. All right, new set of pictures. Each graph above has what kind of degrees? Let's look. Hey, our friend, the parabola, quadratic. Look at this. It looks like a parabola. It's a fourth degree. Let's go higher degree. Check this out, a sixth degree. It looks like a parabola. I wonder if that's a pattern about anything with an even power. Even power. Matter of fact, they almost look the same on your calculator, except they kind of get spread out down here because you're going to find out that the power tells you how many times the function can turn. So obviously a second degree, as it comes down, it can only turn once. But a fourth degree could turn, you always go 1 degree less than that, could turn 1, 2, and then 3. It could look like that, but see, you don't have any more terms. You only have the first term. You only have 1x to the fourth, so it's not that. You won't see these turns. You won't see them if you don't have a bigger number in front and you don't have other terms afterwards. But the first term looks very much like the x squared. They're pretty much related. We call this an even function. And we learned in another lesson that it exhibits symmetry about the, where's my symmetry right now? Where can I cut it in half? Anybody? The, yeah, the x equals to 0. That's called the y-axis. Yep, y-axis. Now that only applies when there's no other terms, okay? That only applies when we're looking at ax to the whatever n is 2n, so I'm make sure it's always even. It only applies x to the 2n. Doesn't matter what a is. Once you start adding other terms like x to the 4, 5, and x to the plus x to the third. Once you start adding more terms, things change, okay? But we're just talking about these. Look at the domain. Looks to me like the domain is every x value to the left, even though if it rises slowly and goes to the left slowly, it still gets there. Eventually, it still gets to the right. So we say its domain is negative infinity to infinity. But we have a restricted range. Restricted range because I don't see any y values below 0 in any of these. So we say that's a restricted domain, and it always seems every one of these seems to start right here. The lowest is at that origin. So we're going to say restricted range of. Oh, I can put a bracket. Bracket 0 to infinity. Now, if we're going to talk about what if a is negative, that flips it. We're going to talk about that in a minute. These even functions are also continuous on the entire domain. Thank you. We can see that they are continuous. There's no breaks. There's no jumps. There's no asymptotes. However, they are what word did I? Oh, from negative infinity to 0, the function seems to be decreasing. If you look at it, it's decreasing. Once I get to that 0, it increases. So I go increases on 0 to infinity, forever and ever and ever, appearing as though they fall. No, to the left. That would be rise to the left, and it rises to the right. In other words, it appears that it goes up forever that way and up forever that way. It appears to do that. Okay, so that's a lot of gobbledygook. I am so happy to hear you ask that. You just made my day. Who was that?
I think it was Thomas.
Was who?
Thomas.
I can't hear you, Moses.
It was Thomas.
Ann. Okay. Good job, Ann. What? Somebody's coming in the room now?
Thank you. I'm finished.
No, not a problem. That makes my day because it really does mean at least one person is doing their notes. And have I given you your quiz on notes yet? All the other classes have got one. Maybe I didn't give you one yet. Pictures over here would have flipped over, flipped over, flipped over. Even these would have flipped over. That would have gone here. That would have gone up there. This side would have gone up there. That side would have gone here. They all would have. Where are we now? Graphs. Yes.
Could you please go back to
Sure.
the page I wasn't finished?
And, yeah, that's where I'm at. Graphs of general polynomials. Okay, so we're looking at that again, except now he's adding some stuff. We're going to talk about what happens to A. We're going to talk about what happens if I add a number. We're going to talk about what if I add a number into the x. Okay, just like we did with our parabola. When the A is greater than 1, and I do the absolute value, it doesn't matter if it's a -5 or a 5. The graph is stretched. I think the word you're looking for is vertically. Vertically. Making it, when you pull something vertically, remember what it does? It makes it what? What's the word I could use? It makes it, what's it doing to it? Shrinking? As you're pulling up, you see a shrink? Where's the shrink coming from? So I don't want to say you're wrong, because you are right. It is shrinking horizontally. A vertical stretch shrinks it horizontally. I think the word they want you to say is it makes it narrow. I like to use the word skinny. When you pull something up and stretch it up, it makes it skinnier or narrower. If the absolute value of a is a fraction, that means it's between 0 and 1. Doesn't matter whether it's a negative half or a positive half. That graph is, I'm not sure how he filled in the words. I'm going to say that graph is fat, or maybe that's not a very polite word to use anymore. It's fatter, or I can say it's a vertical shrink. Well, maybe that's what they want here, making it wider. I don't know. I don't know what he really wanted. To me, I've said enough. You understand that if y equals 1/2 x squared, we've learned that that regular parabola looked like this when I got done with it. It got wider. Still had the same vertex, but that's what happened. It was a vertical shrink and got pushed down and it got wider. Now, if we put a negative in front of a and there's no absolute value, you have to realize that whenever I put a negative in front of anything, it causes it to flip over the x-axis. So we call that a reflection. It's reflected across the x-axis. And that's if I put a negative in front. Every one of those pictures we saw on the other page, every one, okay? If you go a plus k added to any of those polynomials, you remember what plus k did for our parabola? It shifted it which way? It shifted it k units up. Thank you. I saw somebody post, Rebecca. It does shift it up. I won't always see your messages in the Zoom because I'm not looking at my computer. It just so happened it caught my eye. So k units up. Thank you, Rebecca. If k is greater than if k is greater than 0. Okay, I was assuming it anyway. K was going to be 0, or else he would have put a minus here. But anyway, he could have said plus -2. That means k would be negative. But right now, I got lucky. K was positive. And it goes k units down if k was less than 0. And I guess Rebecca thought the same thing as me too, well, how we were looking at it. The graphs of f of x equals a on the outside. Now look in the parentheses, x minus h. We've had this before. I don't know, it's like the 5th time that we've talked about inside the parenthesis. I could have a ax plus an h. I could have an ax minus an h. And I realize that I always have to pretend that there's always a minus built in. So this actually was a minus h. So h was actually negative. And this was actually a minus a positive h. So h is actually positive. And I've learned that when I see x plus h, I have to think the opposite because a plus really meant minus minus. So that meant it shifted left, as I recall. And when I see an x minus the h, I have to think plus, so that shifts to the right. So that's what we're doing right here. It's shifted, if h is greater than 0, that means if h was positive, it's shifting left. He's using the word translated. It's shifted, I think he wants me to go h units left if the h was positive. And then I go h units to the right if h was less than 0. That would have been, if h is less than 0, that's a minus minus. That's why it looks like it's positive. So it's shifting. Well, do I have it right? h is positive, which of these is h positive? Left or right?
Right.
The right. Remember, you always have the x minus built in. So whatever number I put here, if I put a positive number, she was already in the room. She must have got kicked out. If I put h here as positive, then we know I'm going to the right. And that negative there is built in. If I have x plus the 2, then you have to remember that was really x, that minus is built in. That's really h is a negative 2. So I move left. So when h is positive, you are moving to the right, but you see a negative. Let me make sure I got that right. If h is positive, I think I wrote it wrong. H units left. If h is, yeah, that was wrong. Does anybody agree with me that I'm wrong? I'm going back to my cheat sheet here. I don't like how they're doing it. When I see, to me it's so much simpler to say, when I see x minus 2 to the 5th power, I know it moves to the right. But then I have to remember what value is h. H is a 2. When I see x plus 2 to the 7th power, then I know it moves left because it's the opposite sign. So that really meant h is negative, x minus 2. So I have to make sure I say that right. So if h is positive, which is this example right here, h is positive, I move to the right. H units right. If an h units to the left, if h was negative. But it doesn't look like it because we keep seeing this minus here, so it kind of confuses us. What if I do, let me erase my chicken scratch here so I can answer that last thing. The graph of f of x equals, there's an a, there's a minus h, there's a plus k here. Shows a combination of these. The generic word for everything that's happening are called translations. It just means things are moving around. Things are flipping, things are stretching, whatever. You ready for your first problem? Now we're doing it by hand. Calculators, I know in real life nobody does this by hand, but I want to show you some techniques. I have no idea what just came up, and how did that come up? Oh, I guess it's a pointer. I didn't know I even had a pointer. Oh, I learned something. All right, so I'm going to show you some things that I do if I want to graph this by hand. First of all, pay attention. That's an odd power. Also pay attention. There's a positive number in front. So if I wasn't even graphing it on the grid, it has to look something like this. It has to fall to the left, rise to the right. I just have to figure out where does it go. And I see a minus 2 here on the outside of it. So what that meant was, if the parent looks something like this at 0, 0, then that 0, 0 has to move down 2. So I know that picture is going to have to look something like that. Look very similar, but shifted down. That meant shift down, vertical translation down. But here's what I always do. I always find two important points. My y-intercept, we do that one first. That happens when x is equal to 0. So what I'm asking you is, can you evaluate f of 0? Which means 0 to the 5th power plus 2. What is 0 to the 5th power plus 2?
-2.
Oh, yes, thank you very much. I'm blinded. What is 0 to the 5th power minus 2?
-2.
-2. So I know at 0, -2 is a very important point. 0, -2. It sort of reinforces what I said about shifting down, doesn't it? Now what do? I talk about the x-intercept, if I can find it, if I can get it, or approximate it. That means your y has to be 0. So what I do is I say 0 is equal to x to the 5th minus 2. And then I say, how do I solve that? Well, I add 2 to both sides, is x to the 5th. To get rid of x to the 5th, I do the 5th root, which means this, 5th root, the house with a 5 on the inside, and I do it to both sides. That gives me x is equal to something, okay? By the way, it's going to be very small. Here's how I know. 1 times 1 times 1 times 1 times 1 is still a 1. There's 1 to the 5th power. So it can't be a 1. I need to get closer to 2. So let me try the 2. 2 times 2 times 2 times 2 times 2 is 4, 8 is 16, 32. So I need a number between 1 and 2 to give me this inside number. I don't know what it would be, but it's got to be bigger than 1, but less than 2. Because 5th root means what times itself 5 times gives you this number. Has to be between 1 and 2. So what I'm going to do, I'm going to go over here when the y is 0, and find something between 1 and 2. I'm going to call it right here. Do I know really what it is? No. But it's close enough for my government work, okay? So now I have the 2 points I need. Now, just for fun, let me see what happens if x is equal to 2. And I key that in. F of 2 equals 2 to the 5th power. Is that what it was? Yeah, 5th power minus 2. 2 to the 5th power minus 2. 2 to the 5th is 32. We just did that a minute ago. 32 minus 2 is 30. Do you realize that when x is equal to 2, I have to go all the way up to 30? Wouldn't you say that's very skinny then, to be way up there? So here's what I'm going to do. I know this function is going to be skinny going up and skinny going down. So I am just going to do this. Go skinny going down, scoot over, go through that point that I approximate, and skinny going up. And I bet you any money, if you graph that with a calculator, this picture is not too shabby. It's pretty good for by hand. I didn't need a calculator. Calculator would have been easier, sure. If anybody wants to test it out and literally graph it with their calculator, and if I'm way off, somebody can tell me, yeah, I'm way off. Feel free. And I'll have to check it with my calculator, and you'll get extra credit. Okay, let's do B. This is the whole quantity to the 6th power. And I know it's an even power, so guess what? Both sides have to be going up, or both sides have to be going down because, well, the A is a 1. It's positive. Both sides are going to go up. You understand what I'm saying? So I have an idea. It does not shift up or down because there's no number being, there's no K. There's no K. But there's a number inside. Plus 1. The normal going up would look something like this. But this has a plus 1, means to the left 1. So this thing is going to shift to the left somehow. Okay? So let me do it by hand and see if we can come up with something that looks like that. First thing I do is what happens when the How did I do the other one? I did my y-intercept, remember? My y-intercept happened when x is 0. So f of 0 will be 0 plus 1 to the 6th power. What is 0 plus 1 to the 6th power? 1. So 0, 1 is a point that I'm going to put on here, just like I did before. 0, 1. There's my y-intercept. And let me find my x-intercept. X-intercept occurs when the y value is 0. So I say let 0 equal to x plus 1 to the 6th power. To get rid of the 6th power, I 6th root it. 6th root both sides. That cancels out the power, x plus 1. And the 6th root of 0 is 0, because 0 times 0 times 0 times 0 times 0 times 0 is still 0. So I solve that for x. X is a negative 1. Do you see that? So I go to my picture, and I say I have a point over here. That looks very similar to what I just did a minute ago about shifting to the left 1. I have a feeling that this is sort of like the vertex that I just found, because it doesn't shift up or down, remember? Remember I said it doesn't shift up or down? So that must be the lowest point it can be. So that makes a point to the right. That would be my line of symmetry. We draw it in yellow. Is it drawing? I don't see it. There it is. That's my line of symmetry. That must mean I have a point right here as well. Let me prove it to you. Let me plug in a negative 2. I always find one more point. What if x is a negative 2? So f of a negative 2 means negative 2 plus 1 to the 6th power. What is a negative 2 plus 1? That's a negative 1 to the 6th power. What's a negative 1 times 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 a negative 1? 1. That ordered pair is negative 2, 1. Exactly where I put the yellow circle. Negative 2, 1. How did I know it was going to go there? Thinking about the symmetry, thinking about the lowest place was 0 anyway. So that's enough to give me a sort of like a parabola. You want another point over here? Feel free. You want to grab a positive 2 just to see? You can do that. How accurate do you want it? What if x is 2? That gives me f of 2 then would be a 2 plus 1s to the 6th power. Now you may not want to do this because our brains don't work very high with the 6th power. 2 plus 1 is 3. 3 to the 6th power. I have no idea what 3 to the 6th power is. I'd have to beg you to use a calculator. Can someone tell me what the 3 to the 6th power? I know it's pretty big. 3 times 3 times 3 times 3 times 3 times 3. That's 9. That's 9. That's 9. That's 81. And that is how much? 2 what?
729.
729. It's ridiculous. Could I even find that on the map at 2? Could I find 700? No, I can't. So what I want to do is make this super, super skinny going up. And use symmetry. Go 2 to the left and also realize that this thing is going to go super, 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 super skinny going up. Now, I don't know how accurate that is. I didn't use my calculator. But I bet you it's pretty close. And here, guys, the most important points was this one here, the x-intercept, and the y-intercept. They were very important. So I think it's okay. It may not be perfect, but it's close enough for the government. They won't fire you. All right. Now we're going to put a bunch of stuff together. What do I notice? It's a cubic. Normally, a cubic does this, falls to the left, rises to the right. But there's a negative out front. right away that causes it to flip, right? So I can erase the evidence. And then what else do I notice? What else do I notice? Up 3, right 1. You see that? Right 1, up 3, and there's a 2. That means it got a vertical stretch. So I'm going to take this point. It's going to go to the right 1. And it's going to go up 3, up here. And it's going to be a vertical stretch, means it's going to be skinnier than what I'm looking at. So how can I make it skinnier than what I'm looking at? I'll go like that and like that. It's kind of hard. It should be skinnier than that. But let's see how it looks. First thing I do, I find my y-intercept. That happens when x is 0. So f of 0, in this case, would be a negative 2, parenthesis, 0 minus 1 cube plus 1. 0 minus 1 is a negative 1. And you need to realize that when you cube a negative number, it's still negative, because a negative times a negative times a negative is still negative. So that's a negative 2 times a negative 1 plus 1. 2 plus 1. 3. Interesting. I told you up 3. And look where I'm going. 1, 2, 3. Instead of 0, 0, where the original would have been. Okay. I didn't get it to move. And did I do the math right? I did 0 minus 1. I cubed it. That's a negative 1. That's a 2. Oh, no, I did it wrong. Nobody told me. What happened? I see the error. I think I did. I see the error. Do you see it? Okay.
The yellow dot, yeah, it's there.
Huh?
The yellow dot is there.
Yeah, but see, I didn't write it right. It's not plus 1. It was a plus 3. Nobody caught that. Should be up 5. That point went up 5. 1, 2, 3, 4. It went up to here. To 5. So that point really was not just the origin moving. That was something else happening. Okay. What else do I find? Let me get rid of that. Oh, that won't let me. Okay. So I got 0, 5. Now I need my x-intercept. How do I do that? I let y be equal to 0. That's my x-intercept. So 0 is equal to a negative 2 times x minus 1 cubed plus 3. That's going to be a little harder because I got a lot of stuff to do. Add 3 to both sides. 3 equals to negative 2 x minus 1 cubed. Divide both sides by a negative 2. That's a negative 3 halves equals to x minus 1 to the third power. To get rid of the third power, I cube root both sides. And you are allowed to cube root a negative. You can do an odd power root on a negative number. That gives me x minus 1 equals to some negative number of whatever the cube root of 1.5 is. And I'll be honest, I don't know what the cube root of 1.5. But I can guess because watch. 1 times 1 times 1 times 1 is 1. I need bigger than 1. 2 times 2 times 2 is 8. I need smaller than 2. So the answer is between 1 and 2. So if this answer is between 1 and 2, between 1 and 2, with a negative in front, that would be between what? A negative 1 and a negative 2. That's where I'm at. But now I have to add 1 to both sides. So in my head, if I add 1 to both sides, I'm probably looking at something, if I did it right, I'm probably looking at something between 0 and a negative 1. But let me have you help me out with a calculator. Could somebody pick up a calculator and actually do the cube root of 1.5 times a negative 1? Do you know how to do the cube root with your calculator? You probably have a cube root button, but if you want to do it without thinking, just take 1.5 and caret 1 divided by 3. That's the same thing as a cube root. Anybody? You're going to make me pick up my calculator? No one's going to do it? Say it again. 1.144. And then I put a negative in front? Okay, thank you very, very, very much. Who did that? Louder, I can't hear your name. Did you hear it, Moises? Until, okay. She sounds different today. Now I have to add that 1 to both sides. So if I add 1, that gives me a negative 0.144, which is what I said was between a 0 and a negative 1. That is between 0 and negative 1. So what am I going to do? Go to my picture. I didn't really have to know it. I just had to know it's around here. So I'm going to put a dot between 0 and negative 1. And remember what we said about the cubic. It starts at the bottom and goes up. So here goes. How am I going to get from here and then over? Whoop, what happened to that point? It disappeared on me because I hit the eraser. All right, here it's going to be hard. It's going to be hard. I'm going to start here and start going down from this side. Then I'm going to scoot over and start going up to this side and continue. So I could have probably done it smoother, but I didn't. It's going to look something like this. There's that little turn in there. And it looks skinny. And I was expecting it to be skinny because there's a 2 in front. And if you use your calculator, if you prove me wrong that I'm way off, I give you points. And I think I'm off. I think I'm on the wrong side of the axis. What did I do wrong? Yeah, I don't think this point is right. I think I'm off in my math here. Let's see again. I caught mine. I'm plugging in a 0. Where? Okay. X-intercept where I set it equal to 0. Oh, I see what I did wrong. I see it. Anybody see it? Wait, no, I have it. I did minus 3. Minus 3 divided. Ah, I see it. Somebody tell me so I can give you points. Until you got it. I know you do. Okay. 5, 4, 3, 2, 1. I did not divide by a negative 2. That's a negative 2. I did subtract the 3, giving me the negative 3, but then I had to divide by a negative 2, so there's no negative in front. There's no negative in front. So she's still right. The answer was positive 1.144. And now when I add 1, I get a 2.144. So up here, I need to hide the evidence. You guys could have found it. You could have got some points, but you didn't want it. 1.144 would be over here. And so now it still falls this way. Oh, obviously it flipped. I forgot about the flipping part. Then it comes up and has to go over to here. Well, that's too skinny. Hold on. It's hard. Let me erase that up there too because it's affecting my thought process. Okay, here it goes. It's got to come up somehow. Got to come up and it's got to go over. And then it's going to have to go up some like skinny. All right. I would mind it if somebody would plug it in the calculator and see if it looks something like this. If anybody sees it. All right, moving on. Okay, it's amazing. Feel free to talk out loud, guys, because I did skip this page. Okay, thank you. You know what? I did this yesterday too. Unless otherwise restricted, the domain of a polynomial function is the set of, I'm going to use it in words, all real numbers. That means negative infinity to infinity. Polynomial functions are smooth, they're continuous, always on the interval, since it's all real numbers, negative infinity to infinity. The range of a polynomial of odd degree is also the set of all real numbers, because the odd went from negative infinity to infinity as well. If it's an even function, the range switches. The range goes, well, the range is restricted. It goes from, for any real number k, it goes from k, I'm not even sure what he's saying, k to infinity, or it can go k to a negative infinity, because it could be the highest or the lowest place. Remember, it can go that way, or it can go that way. So it could be k is the lowest place here, and it can go forever up. Yeah, stop. Probably when it shut off. Okay, so look at the behavior. If you got a function that looks like that direction, then you know its end behavior is infinity when you're going to the right. And you know that if it's going down forever, your end behavior is negative infinity. That means how far down will it go? To negative infinity. How far up will it go? Positive infinity. If it's flipped, because there's a negative a, then it could go, as you go to negative infinity, the end behavior is infinity. As you go to infinity, the end behavior is negative infinity. And he's also telling you, this is, I don't know why I was talking about end behavior. I thought we were going to talk about end behavior. He's talking about the zero. So he just wants to talk about the zero. Obviously, I have one zero. If it crosses the axis, that's 1, 0. If a function bounces off the axis and goes back up, that's a multiplicity. You could have more than 1, 0. You could have it could be x equals to 2 3 times, or 2 times, or 5 times. Just depends on how many turns that polynomial could have had. But if it goes straight through, that's multiplicity of 1. The 0 is at c comma 0. Whatever that number is, c, the height is going to be 0. This c comma 0 could be there many, many times because it bounces off. This one, it seems to be, he's calling it tangent to the x-axis. That means it gets there and it rides it for a while and goes up. So what can happen here at C0? If C is a 0 of an odd multiplicity greater than 1, the graph wiggles at C. Is that what he wrote? Wiggles? I've never used that thought. Wiggles at C. If it was an odd multiplicity, like 3, 5, 7, that one I've never asked anybody for. All right, thank you for telling me that I'm turning points and end behavior. Interesting point here, that your functions have turning points. I already explained to you, so I said it once, but let me write it here. A polynomial function of degree n has at most n minus 1 turning points. It can have less, like the x to the 5th power. did not have 4 turning points. But if I put numbers in front and add more to the polynomial, it could have 4. At most, n minus 1 turning points. If your n behavior, okay, if your a is, what's he looking at? You flip the bottom part. Are we referring to what? The last problem? Yeah, I did have it on the wrong. I did flip that over because I lost my negative. Oh, I skipped a page. Talking about that. This was where I was talking about turning points. Now we're going to do n behavior. Okay. N behavior, you got ax to the n. That's the dominating term. That's your first term. If a is greater than 0, then as x goes to infinity, since it's we're talking about what kind of function? Odd? Yes. We're talking about odd. That means ax to the 5th, ax to the 3rd. Then we know it does this, guys. And if a is greater than 0, it falls to the left and rises to the right. So as I go to infinity, as x goes to infinity, my y values, let's see, how is he wanting me to write it? And x goes to negative infinity. We symbolize this behavior. I'm not really sure how he's wording it or how he's writing it. Maybe he's asking us to talk about like a limit problem. Yeah, I don't know how he's addressing it. I don't know how. If a is greater than 0, then as x approaches infinity, I'm going to say f of x approaches infinity as well. As you go to the right, you're also going up. And as x approaches negative infinity, as I go to the left, my y value is going down. So I'm going to say f of x is approaching negative infinity. We symbolize its end behavior as, you know what, I'm going to write this. I don't know if he does it in the book or not. The limit as x approaches infinity of f of x, in this case, will be infinity. The limit, the number, as x approaches negative infinity of f of x will be negative infinity. That's what it means. As I approach a big positive number, my y value is a big positive number. As I approach a negative number, big negative, then my y value is also big negative because the function does this, remember? That's odd. Let's look at the next one. If we're still doing odd, so I think what I just did both of them together. I think I did both of what he's talking about in that first line because I just don't know how he wanted it. So I'm just going to say all you need is that number 1. Oh no, this is a is less than 0. Sorry. If a is less than 0, then this shape, this S shape, flips. So what it does is it changes it. Okay, if a is less than 0, then as x goes to negative infinity, as I go to the right, my y values go up. So I'm going to say f of x approaches infinity now. As I go, he said I'm going to the right. No, I'm going to negative infinity, sorry. He's doing this side. As I go to infinity, as I go this way, I'm actually going down in the y's. Let me add in a negative there. And as x approaches to the left, then my f of x is going up. All right. We're not finished with it. I'll have to send you the completion of it because I want you to have this finished. I got one question for the class, though. Does anybody want an optional center review problems to work on that I'm not going to make you do if you don't want to? Okay, I got one yes. All right.
Yes.
Make sure, guys, most of you are supposed to be doing your mentor, what is it called? Cyber mentor class. You were supposed to get a message from your second period teacher that you have to sign up and go to a different Zoom. Did you get all that, guys, from somebody?
I think some people did.
Okay. I'll see you guys. I'll give you the review so you can study for your test.
Bye, sir.
Bye. Okay, I know I rushed at that one part. We symbolize the end behavior. This is when A is a negative number. So remember what the picture looks like. It's an odd degree, so it looks like that. So I'm going to symbolize it as the limit as x approaches infinity. That means to the right of f of x, then that is always going to be negative infinity. The limit as x approaches negative infinity means I'm going this way, so my y values are going up to infinity of f of x is infinity. All right, suppose that a of x is the dominating term of a polynomial of f is even. All right, so we're looking at two possible cases, both sides going up or both sides going down. And I have all these extra terms to show you that you could always have more than just the one term that the ones look like in the paper that we had. So anyway, if A is positive, now you know this means it's going up, no matter how many turns you see. Then as x approaches infinity, it doesn't matter whether it's the positive x's or the negative x's. That's why he put the absolute value. Then we know that f of x is approaching infinity. That means it's going up. We could have wrote that. We could have said it opens up. Matter of fact, I'll put that there. Opens up. We symbolize the end behavior as the limit as x approaches plus or minus infinity. Both sides of f of x will be infinity. End behavior. If a is less than 0, that means inside there is a fraction. That means from both sides, that picture looks like this. So it doesn't matter whether I go positive x's or negative x's. Both sides opens down. So I'm going to write, as that occurs, as x approaches infinity or negative infinity, I'm going to say f of x approaches negative infinity, or I could say opens down. We symbolize the end behavior as, where did I want to write that? Right here, as the limit as x approaches plus or minus infinity of f of x will always be negative infinity because it opens down. So the end behavior talks about what happens in the future, what happens in the past, the ends. All right, so determining the end behavior. Example 2, the graphs of the polynomial functions defined below A through D. All right, so this ought to be fun. Okay, so we know the first one, does he give me a name of it? He just give me a picture. Oh, I want to match them up, I think. Matching game. This ought to be interesting. Let me start with this first one. It's positive, so they both have to open up or both have to open down. So right away, I know the answer could be A or it could be C. Since since it's an even power. That's what I meant to say. And since it's positive, has to open up. So I would say this one has to match up with C. That matches C. Let's go over to G. G is another even power. Has to open both up or both open down. There's only one answer left that does that. And since there's a negative there, it opened down, so that would be the A. And this is a third degree, so what it's positive 3 means it looks like this. So it has to rise to the left and fall to the right. The only one that does that is D. H, it flips it. So instead of rising to the right, it falls to the right and rises, or falls to the left and rises to the right instead of rises to the left like the other one did. Plus, it's the only other odd power there is. So that would have been, wait a minute, did I do it wrong? Oh, I wanted this one. I wanted B. CADB. Double check. See, even, opens up, opens down, so C, A, okay. Odd and odd, positive, oh, I'm sorry, positive starts from the bottom and goes up. Did I write that? I wrote it wrong here. I can see where I wrote that. If I wrote that for that, I was wrong. It has to fall to the bottom and go up, so that would have been, H would have to have been B. Okay, well, maybe I wrote B. I can't tell what I wrote. B. This would have flipped it. Oh, maybe I was writing it flipped. I don't remember. Have to look like that. That would be the D one. Yeah, I was on there. I somehow flipped my mind. I don't know. That's what happens when you get old. Okay. Highest degree. Well, it just tells you. You either have up, down, positive, falls to the left, or rises to the left. That's what happens with your pictures. Graphing any polynomial. Okay. I already gave you some of the steps. I truly believe what I said was still going to be true. How many steps do they want? Only 3? I don't know. I definitely find exactly what I did when I was graphing it. Find y-intercepts. Intercept. There's usually only one. Okay, find the y-intercept. That means when x is equal to 0. F of 0 is what? Then we find all the, we call them x-intercepts. Find x-intercepts. Those are also called our zeros from the other lesson we had. Those are called our zeros. And we're only looking for the real zeros if there are any. Okay? And so find all those, plot those. Next set is realize the sign of the plus or minus that first term. So that way you can decide what's happening at those zeros. Are we going to go, which way am I going through them? From the up, down? So I would look at that leading. That gives you a lot of information. Also, we could do a step 4. Identify the end behavior. That helps us predict which X do I want to plug in to see what it does. Okay. Identify the end behavior to see what's happening. Okay. Page on here. Oh yeah, example. Here we go. Graphing another one. I guess we're still doing them by hand. Let's see. Well, let's practice what I preach. Let me find my y-intercept. That means that step will be f of 0 is 2 times 0 cubed is 0. 5 times 0 squared is 0. Minus 0 minus 6. So at 0, 6, I have a point. That's not 6, it's negative 6. That's a negative 6. That's my point. That's my y-intercept. So it gave me a lot of room here. So I'm on my own. Make a graph. 0, 6 is about, 0, negative 6 is about down here. So my next step, let's see, he probably uses the next page. So here, I'm taking my 2x cubed plus 5x squared minus x minus 6, set that equal to 0. Finding my zeros. Can you factor it? Probably not. It's a cubic. Most people can't factor cubics. But what we can do is use the lesson we had on zeros and say, how do I find some zeros? Remember this negative 6 is where I get all my p numbers. They come from the factors of a negative 6, which are a 1, a 6, a 2, and a 3, and then obviously a negative 1, negative 6, negative 2, negative 3. Then this, my number here is my q, and q's will be the factors of a 2, but I don't go plus or minus 1s. I just say 1 and a 2. And remember my possible zeros are all the factors of p over all the factors of q. So if I start listing them, I got a 1 over a 1. That's a 1. I got a negative 1 over the 1. That's a negative 1. I have a 6 over a 1. That's a 6. I have a negative 6 over the 1. That's a negative 6. I have a 2 over the 1. That's a 2. Negative 2 over 1 is a negative 2. I have a 3 over 1. That's a 3. I have a negative 3 over 1. It's a negative 3. I also have, that was all the 1s. I have the 1 over the 2. That's a half or a negative half. I have a 6 over a 2. That's a 3. I already have it. So I already have the plus and minus 3. So then I have a 2 over the 1. That's a 2. I already have it. Or 2 over 2 is a 1. I already have that. 3 over a 2. I don't have that. 3 over 2 or a negative 3 over 2. So there's a whole bunch I could try. How do I try them? We try them with our synthetic division. So my numbers I use is the 2, 5, negative 1, negative 6. So 2, 5, negative 1, negative 6. And a cubic has to have either 1 real root or 3 real roots. Can't have 2 because if you have 2 real would imply 1 complex because you need 3. Why do I need 3? The powers of 3. There's 3 zeros. So, but it can't be 1 complex because complex comes in pairs. So you can't have 2 real and 1 complex. You're going to have 1 real with 2 complex or 3 real. It's the only combination. So if I can find a real, then I can find the other 2, whether they're real or complex, by factoring it because it'll take it down to a quadratic. But let me just play around with this. Let me do the first easy one. Try a 1. Try the 1. I'm doing that one right now. So synthetic division. Bring down the 2, 2, 7, 7, 6. There it is. First one I tried. I already have 0. That means x minus 1 is a factor, and the leftovers
dropping it down 1 degree from the quadratic, right here, the cubic, you drop it down, it becomes, the leftovers become 2x squared plus 7x plus 6. There's my new, there's my original polynomial, f of x. Now, if I was smart, I would just try to factor this quadratic. But I'm a glutton. I'm going to keep trying a few others. I might get lucky. Let me try the 1 again. On the leftovers, 2, 7, 6. 2, how hard could this be? 9. No, that didn't work. Not a 0. So that was pretty much a waste of time. Let me try a negative 1. Negative 1 could work. 2, 7, 6. 2. Negative 2. 5. Negative, oh, that doesn't work either. Okay, what am I at? I did those 2. Let me do the 6. And if you get bored, then you can quit and just factor, which if I was smart, I would just factor if it factors. If it doesn't factor, I could use quadratic formula. So I'd have been done by now. 2, that's 12. Oh, no, that's 19. 19 times 6 is 60 plus 54. 114 adds up to 120. Definitely not a 0. Okay, last one. I'm not going to play around with this. Negative 6, 276, 2, negative 12, negative 5. It's not working either. So I know it's not working. So I know when we should give up on trying to find them. Or do you want to keep going? I did this one, this one, this one. I got 2 more easy ones to do. Let me try them. I just don't want to stop. I get so, I know it'll work. Oh, no, I don't know. You're just guessing. You're just guessing. So bring down the 2. That's a 4. That's 11. That's 22. That's 28. Definitely not. This I promise you. Last one. Last one I'll try because my finger's getting sleepy. 2, negative 4, 3, and I got lucky. There it is. Woof. Found a 0. What does that mean? That means my f of x now is equal to x plus 2, and I had my x minus 1, and notice what's left over. Notice what's left over. Remember, I started with a cubic, then this becomes the quadratic piece. Well, then the answer to this becomes the linear piece, 2x plus 3. So I have it. But let me show you how dumb I was. I could have just taken my 2x squared plus 7x plus 6, set equal to 0, and I could try to factor it. If it doesn't factor, use quadratic formula. But let me try to factor it. 2 times 6 is 12. Factors of 12 that could add up to 7 is 4 times 3, adds up to 7. So that's what I wanted. So my factored are 2x plus 4, 2x plus 3. This reduces by a 2, so it's x plus 2 and a 2x plus 3. There's the x plus 2 that I found right with this x equals to a negative 2 means x plus 2 equals 0 is the factor. There's my leftovers. Do you see it? 2x plus 3. So 2x plus 3 equals to 0 means x equals to 3/2. Actually, negative 3/2. Is that correct? negative 3/2. So I have 3 factors. I have all 3 of these here. Let's see. This gives me x equals the negative 2. This gives me the x equals to a 1. This gives me x equals to a negative 3/2. Those are my zeros. So go to my graph and find my negative 2. 1, 1, 2. Find my negative 1.5. So that's a negative. So it's somewhere here. There's my negative 2. There's my negative 3/2. There's my positive 1 over here. So what does this function look like then? Well, this function comes from the bottom left. So somewhere it's coming up. I don't know how high it goes, but it has to come back down to get to this 0 here. It has to go through this 0 here. Then it has to go through the y-intercept, then it has to whip back up and go back to that 0. So that may not be a perfect graph, but it's close enough for the government. All right, let's move on. And yeah, there's step 2 and step 3 and so forth. So step 2 was going to be find my zeros. That means you set the whole function equals to 0. So let me go back to the page. I had more room over there. Plus I have my graph started. Okay, I'm not going to regraph it here because I have it on the page. What if your polynomial is already factored for you? You can look right here and realize that x has to be a 1, x has to be a 3, and x has to be a negative 2. And look at that. There's 2 of them. Remember the lecture we had. This is going to be an x times an x times an x times an x. This is an x to the 4th power. So it's an even power. So we know that both sides go up or both sides go down. Since there's a negative in front, the winner is it's going to open down. Okay? So right from here, I'm just going to go to my, and my first step was y-intercept. So y-intercept still is f of 0. So it's going to be really simple to plug in a 0 for all these x's. I have that negative in front. 0 minus 1 is a negative 1. 0 minus 3 is a negative 3. 0 plus 2 is a 2. And then there's another 0 plus 2 is a 2. So that turns into a negative of a negative is positive 1. Positive 1 times a negative 3 is a negative 3. Negative 3 times 4 is a negative 12. So I know way down here, down south, negative 12 must be my y-intercept. And then I know I have 1, 0 at a 1. So I'm going to go here to 1. Then I have another 0 at a negative 3, at a 3. I have another one at 3. Do I have those two? Yeah, I do have it at a 3. 1, 2, 3. That was a 1. Then I have, that means this, you know that there has to be a polynomial cutting through both pieces. You know that because there's only one of them. Multiplicity is 1. Since this is a double root, at that negative 2, it's going to either hit this and bounce back that way, or it's going to bounce that way. Okay? Now, which is it going to be? Think about what this thing does. We already said it's going to open down. Has to open down. That means from both sides it has to come this way. So look at what kind of a picture I have. And I said this is a double root right here. Change the color. This is a double root. That means as this function comes up, it's going to hit that bounce off. Got to come back down. And then it can't even go that far over because it has to come back up to here. Then it's going to go somewhere. Then it's going to come back down to here and come back down. The question is, what's happening in here? I don't really know. If you wanted to know, we could say, well, what x was that? This x is a 2. Is it going to hurt me to take 30 seconds of my life and ask myself, what happens at f of 2? F of 2 would be pretty easy to do. You still have a negative. You have a 2 minus 1, that's a 1. So that's a 1. You have a 2 minus 3, that's a negative 1. Negative 1. You have a 2 plus 2, that's a 4. And there's 2 4s, so 4 squared is 16. That gives me a negative, negative, and then a positive. So that gives me a positive 16. So it's not very exciting, but what this means is this function has to go all the way up, at least until I'm at a 16. And so then this smooth curve comes down. And it's not a perfect picture if you use your calculator, but I'm going to say the same thing I always say. It's close enough for the government. Just ask Mr. Delegata, he'll tell you it's close enough for the government. And, we're still going on. Oh, that's the same thing, graphing more. Relationships among x-intercept, 0 solutions and factors. C is a 0 of f. That means z is I'm not sure. C is if it's called a 0, it's also called a root or solution, or it's an x-intercept. Yeah, really, he could use any of those words. It's really hard to decide what he's actually trying to put in there. It's a 0. C is also a solution of f of x equals to 0. If you find c is a 0 and you go x minus c would be called, that's a factor. That'll work. New theorem, intermediate value theorem, IVT. And I don't know if we'll spend any time in boundedness, but intermediate is important because it's in calculus too. If f of x is a polynomial function with only real coefficients, for all real numbers, a and b, the values of f of a is f of b. So we're looking at 2 points. If you're looking at on a function, here's a, here's b, and if you look at, he says opposite in sign, what he's saying there is f of a could be up here, there's a point, and f of b could be down here, f of b. They're opposite in sign. The intermediate value theorem said that if you have x is a and x is b, and you plug them into the function, you get a positive number and you get a negative number, then you're guaranteed there has to at least be one real 0 between a and b. Well, look at the picture. If you connect the dots, because it's continuous, he said, He should have said continuous. He said it's a polynomial function, therefore it's continuous. There has to be a 0 here, at least 1 0. Has to be. That's called the intermediate, the in-between theorem. So use synthetic division to show that f of x has a real 0 between 2 and 3. Okay, so it's really simple. Find out what f of 2 is. Find out what f of 3 is. You can just plug it in, but he wants us to use synthetic division. So that means for synthetic division, if I'm going to check a 2, then I use my coefficients 1, -2, -1, and 1. Let's see what happens. 1, this is the same thing as plugging it in. 2, 0, 0, -1, -2, -1. That means f of 2 is a -1. Let's try the 3. 1, -2, -1, and 1. 1, 3, 1, 3, 2, 6, 7. That's a 7. So my 0, how can I write that to tell you? Since f of 2 is greater or less than 0, and f of 3 is greater than 0, there must exist a 0 at x equals to c, where c is, I'm going to put less than b but greater than a. C is in between A and B, such that, there's your such that, f of c is 0. I can't get much more fancier than that. In English, all it means is c is somewhere in between 2 and 3, because I'm picking a 2 and a 3, so these two signs change places. I went from a negative to a positive. Went from a negative to a positive. So there has to be a 0c here. If this a was a 2 and I'm at a -1, and this b is a 3, and that's +7, then there has to be a c in the middle. That's the intermediate value theorem. Very powerful. If f of a and f of b are not opposite in sign, then it does the intermediate value theorem mean that there is no 0 between a and b? False. There could be non-real zeros. All right, last thing here, then I'm going to have lunch. Boundedness theorem is let f of x be a polynomial degree of n greater than 1 with real coefficients and with a positive leading coefficient. Okay, that's important. Suppose f of x is divided synthetically by x is c. Okay, fine. If you were to do synthetic division and you divide by it, if c is greater than 0, okay, that means basically all you did is plugged in the c. You plugged in a number, and you get a positive number. All the numbers in the bottom row of the synthetic division, okay, if c is greater than 0, and all the numbers in the bottom row of the synthetic division are positive, he says non-negative, then f of x has no 0 greater than c. So if f of c is greater than 0, then we check the bottom row, the answers, and check all those numbers. And if they are all positive, then you know that f of x has no zero that is greater than the c that I tried. It's bounded. You know, that's the biggest zero there is. There's no zero bigger. Well, that wasn't even a zero. We're just saying whatever c that was tried. If the c comes out to be a negative number, negative, and the numbers in the bottom row of the synthetic division alternate in sign. That means plus, negative, negative, plus, to be alternating. So if we get a negative answer for f of c, if f of c is less than 0, and we get the plus, negative, what do we know? We know that f of x, let's see, sign with 0 considered positive or with 0 considered positive or negative as needed. So if you get a 0, you can call it whatever you want to make the pattern work. Then no 0 less than c exists. Again, this theorem is only good for if you didn't have calculators, like in the old days. Show that the real numbers of this satisfy these conditions. No real 0 number greater than 3. So let's go ahead, use c is equal to 3. Let's use synthetic division. 2, negative 5, plus 3, plus 1. Let's see what happens. 3 times 3 is, I'll bring on the 2. 2 times 3 is 6. That number goes here. We add it, that's a 1. That's a 3, that goes here. We add it, that's a 6. That's an 18. Add it up, 19. So I know f of 3 is 19. But it doesn't really matter because all I'm checking for is, we're checking the first thing. If c is greater than 0, positive I mean, that's what it means. That's a 3. 3 is greater than 0, so I'm using this one here, okay? And let's look at the bottom row. If they are all non-negative, okay, so that means 0 is not negative, so it could have been a 0. That would have been fine. Positive, 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 positive. They are all non-negative. That means there's no 0 greater than 3. No number, you wouldn't try any other number. Great. So right here, if I was to, well, it's not even a possible. Factors of 1 and factors of 2 never even give me any possibilities of bigger than 3 anyway. But that just shows that there are no numbers greater than 3 as zeros. I would have tried it anyway, because look at, I wouldn't have tried it. I would have tried a 1, or I would have tried a negative 1, or I would have tried a half. That's all, or a negative half. 1, negative 1, 1 half, negative half. I wouldn't even try. Why would I have tried a 4? I wouldn't have tried it. But anyway, he wants me to prove that there's no real 0 less than a negative 1. So now c is a negative 1, c is less than 0. I'm using the second one here. So I do negative 1 going into the 2, negative 5, the 3, and the 1. Let's see. He says show that it's true. So 2, negative 7, 7, 10, negative 10, negative 9. Look what happened. Positive, negative, positive, negative. It alternated, and c is not greater than 0. Therefore, there are no zeros less than what? C equals to a negative 1. Nothing less than. So I wouldn't try them anyway. Wasn't even one of my possibilities. Anyway, well, negative half was. This proves that no, negative half is still not less than negative 1. That was a dumb problem because none of them. I would have tried them anyway. And the last part is just use a calculator. Just use a calculator and try to approximate the zeros. I can't show you on a calculator, not recording the way I am, but maybe I can do it in a Zoom and show it to you. But I'm going to call it quits. That's a lot to get. So have a good one through for your test.